right, hi again. We're going to keep going with chapter 6, where today we're going to normalize the Boltzmann probability and develop what's called the canonical partition function. That's the normalization factor for the Boltzmann probability. We're still working on sections 1 and 2 of chapter 6 in Schroeder. Let's review what we did last time. So we developed the proportionality form of the Boltzmann probability, and the big deal about it was that we were able to connect microscopic parameter E sub s associated to some small subsystem with macroscopic parameter of a reservoir with which the subsystem is in thermal equilibrium. And so the goal for today is to find the normalization factor. That's going to give us the probability in complete form. And we're going to also really start to develop how the normalization factor is useful and interesting just by itself, which is pretty surprising. All right, so let's start to normalize this probability. It's a pretty easy calculation. You should do it yourself for sure on your own paper, even if you think it's too easy for you. So we start with Boltzmann probability, and we just write the normalization factor as some number c. Normalization of a probability means that if you sum up all the possibilities, they have to total to 1. And so what that means in this case is that we are going to take the probability of every possible energy level, every possible subsystem energy level, and we're going to sum over all the possible E sub s's, and they have to add up to 1. So let's substitute this c times e to the minus e sub s over kbt into this formula. So we get the c and the exponential summed up equals to 1. And you can factor the c out, and you can say that c is equal to 1 over the sum of all these exponentials. So can we call these exponentials Boltzmann factors? Let's do that. E to the minus energy over kbt is going to be called a Boltzmann factor. So the normalization coefficient is just 1 over the sum of all possible Boltzmann factors for the system that we're interested in. And so we give the denominator, we give the denominator a special name. We say that c is equal to 1 over z, where z is the canonical partition function for the system that we're looking at. And so z is the sum on all the possible energy levels of the Boltzmann factors. And it's really important. It's the most important thing in statistical mechanics. The z comes from the German Zustandsum, which I don't know if I spelled perfectly. That's what it sounds like anyway. I'm pretty sure that it does mean sum over states, because that's what it is. You're summing over all the possible energy states, the Boltzmann factor for each state. So now we have a complete Boltzmann probability. That's just the probability of any energy level is the Boltzmann factor for that energy level divided by the normalization. This is such an important result. This is the key result for statistical mechanics. Probably period. I mean, we're going to add plenty of baggage and applications to it. You have to memorize these two formulas for test 2 and for the final. I will not put these on formula sheets because my view is that you have to be engaged enough with this material to memorize this almost by accident. Yeah. So this might be infinity. You might have to include an infinite number of states in the sum. In practice, that's not really relevant to think about. But this is basically our intuition. At low temperature, only one state is relevant, and that's the ground state with E sub 0 equals 0. By contrast, at high temperature, all the states are equally relevant. They're equally weighted, if you want. inside the Boltzmann sum. And so that generalizes. At any intermediate temperature, the partition function basically counts the number of relevant states when the subsystem is in equilibrium with a reservoir at temperature T. So summarize again, at low temperature only one state is relevant, that's the ground state. At high temperature all states are equally relevant, and at intermediate temperature there's some number of states between one and all of them, right? And how many actually depends on the temperature. Okay, so there's a really important warning that I have to give you. The partition function is sort of counting relevant states, but it is not the multiplicity. You must not confuse the partition function and the multiplicity. They both count things, but they count different things. And more importantly, they count things under very, very different conditions. When we develop multiplicities, we weren't thinking about a subsystem in equilibrium with a thermal reservoir at temperature T. We're just thinking about a system where we need to count all the microstates consistent with a given macrostate. It's very, very different. It's probably easy to confuse at first, and so you need to find a way to force yourself to not think that the partition function is just a different version of the multiplicity. They are not the same. Okay, so let's do an example. We are given an energy spectrum. Note that this is the same as the hydrogen atom example from the last slides. We're given the solution to the quantum mechanics problem. We're given the energy levels. After that, we start doing StatMech. So we're given a system with two levels. We'll call the lowest energy level E sub 0 equals 0. That's here. And we'll say that the excited state is E sub 1, and it's some energy, I think that's an epsilon, I keep calling it E, epsilon, above the ground state. So for this system, we can easily go right in and calculate the canonical partition function. It's a sum over all the states. There are only two states, so there'll be only two terms in the sum. The first term gives us e to the minus beta times 0. Second term e to the minus beta epsilon. And so the expression for z is just 1 plus e to the minus beta epsilon. This is pretty awesome. All right, so in many quantum mechanics problems, I'm going to say quantum mechanics, in many physics problems, there are only a few energy levels that you need to worry about. And so in those circumstances, you can actually just do the sum in the partition function explicitly. Like even if you had 7 energy levels, it wouldn't be too hard for you to write out every single Boltzmann factor and just write the partition function down on one line on a piece of paper. I think that's really awesome. Of course, you can think about situations where you would need to consider an infinite number of states, and there are ways to deal with that. Maybe we'll talk about it in the next lecture. But it's also really, really common that you only need to consider a few. All right. So after we've got the partition function z, which was really easy, one line being overly explicit with the e to the minus 0 term, we can calculate the probability of observing the system in each of the possible allowed energy levels. So the probability of being in the ground state is the ground state Boltzmann factor divided by the partition function. Ground state Boltzmann factor is 1. The probability of being in the ground state is 1 divided by 1 plus e to the minus beta epsilon. Same thing for probability of being in the excited state, only the Boltzmann factor there is not 1 anymore, it's e to the minus beta epsilon. So you can check for yourself two things. Number one, when you add these two things together, they sum to 1. Sorry. And then you can also note that the probability of being in the ground state is always bigger than or equal to the probability of being in the excited state. That's kind of important. Maybe we'll say more about it towards the end. These facts are generically true, not just for this system. All right, so a textbook example of a two-level system is a two-state paramagnet in an applied magnetic field. So that's not the same as a two-state paramagnet that we worked on extensively in Chapter 2, in that we are going to apply a magnetic field, and the magnetic field is going to establish a Zeeman splitting between the spin-up and spin-down directions. So in zero field, spin-up and spin-down have exactly the same energy. In an applied magnetic field, they do not have the same energy. They're Zeeman split. And so you need to go to Chapter 6 of Schroeder and read Schroeder's analysis of this problem. I expect you to have read it. I expect you to be comfortable with doing the StatMech for it, explaining what's going on. I do want to point out that Zeeman splitting is quantum mechanics and not StatMech, right? So Zeeman splitting is just, okay, you've got a magnetic moment that's quantized inside a magnetic field, and you know that it has to have these discrete energy levels. So I'm not asking you to really do this explicitly, but I think it's interesting to go back and check Chapter 2, where Schroeder uses multiplicity to do the same problem. It's a very difficult, lengthy calculation compared to what it is in Chapter 6. And so I'm not going to hold you accountable for using multiplicity methods in this problem, but I do think it's interesting to compare the problem-solving techniques used just so that you get a feeling for how powerful the partition function actually is. I do expect you to be able to do analysis like Schroeder does in Chapter 6 for the two-state paramagnet in an applied magnetic field. So another thing we can do with the partition function with the Boltzmann probabilities, now that we have them completed and normalized, is that we can actually explicitly calculate average values. So once we know the probability of E sub s, we can pretty much do all the statistics that we need. So if we want to calculate the average value of the energy of the subsystem, we basically take the probability of having energy E sub s, multiply by E sub s, and sum over all the possibilities. Excuse me. And so that looks like this. There's not much we can do with it right now. We'll do something in the next slides. But we can also say that more generally, we can compute the average value of any function of the energy levels by doing the same thing, multiply the function by the probability of each energy level and sum over all the states. And so it looks sort of similar. So the average energy is just a special case of the more general F-bar calculation. You're not expected to memorize these formulas. And so if you're really clever, that also means you're not really expected to memorize the Boltzmann probability, but hopefully you get the point that I'm trying to make by telling you to memorize it. So let's compute the average energy of our generic two-level system that we started with. In this case, we use the probabilities that we already calculated and just plug them. So we calculated these probabilities for being found in each of the energy levels. And we're just going to plug these in to this formula for average energy. So the energy of the ground state is 0, and so you multiply it through by the probability, you're going to get 0. Energy of the excited state is epsilon, multiplied by the probability, and so the average energy is just epsilon e to the minus beta epsilon divided by the partition function. So it definitely has the right units. Exponentials are dimensionless, denominators dimensionless, so it's just energy. You can check for yourself that this makes sense in the high and low temperature limits. Right? So the average energy is going to be 0 at low temperature. So let beta go to infinity. Sorry. High temperature is a really interesting discussion. So let's do that on the next slide. And that's one where you're really going to want to think. And you're probably going to want to go back through this and write the work out on your own paper and make sure that you can sort of explain it to yourself. And let's say explain it on paper, because explaining on paper is another way of saying do things like this in an exam setting. So let's look at the average energy of the two-level system in the high temperature limit. So it's sort of tempting to imagine that if you go towards infinite temperature, your reservoir has tons and tons of energy, thermal energy. Oh my God. And maybe the energy is going to really approach the energy of the excited state, E sub 1 equals epsilon. This is not true. This is false. So you really need to get away from the idea that temperature and energy are the same, and that if you have infinite temperature, you should go to the highest possible energy. That is conceptually completely faulty. This is the formula for the average energy. Let's now take the limit of infinite temperature, and that means we let beta go to 0. And so in that case, you get e to the minus 0 times epsilon divided by the partition function. So that comes out to epsilon in the numerator divided by 1 plus 1 in the denominator, epsilon over 2. So the average energy in the limit of infinite temperature is right down the middle between the two allowed levels. So there is no allowed energy level there, but that is the value of the average energy. And so the correct conceptual way to view what's going on here is that you came into this system and you measured the energy of the subsystem, say 100 times. Okay? And about 50 of those observations, you found the energy was 0 in the ground state. And about 50 of the times, you found it was epsilon, the excited state. So when you average all of those 100 measurements, you'll get that the average energy is about halfway between the two. Okay? It's really important that you're comfortable with this analysis. And it's especially important that you make sure that you're not succumbing to the temptation of imagining that high temperature means highest possible energy. Infinite temperature means all states are equally likely. You will be found with the same probability in the ground state as you will in the excited state in the limit of infinite temperature. So important to pay attention to that. So this last idea kind of leads us into a sort of advanced topic that I want to mention, primarily for the reason of establishing vocabulary, and that's ensemble theory. So ensemble theory is the idea that what we're doing when we're taking those averages using the Boltzmann probability is we're sort of imagining that we have a large number of copies of the system that we're working with. Now we'll consider the copies identical, but only identical in the statistical sense. And so that means that identical means they have the same P of E sub s. It does not mean that the subsystems will all be certainly found to have the same E sub s energy. You get the point? They're identical in their statistical properties, their probabilities, not in their actual realized properties. And so we call this quantity that we've already defined an ensemble average, where we're sort of imagining that we've made all these copies. Each one has an E sub s value that correctly describes the P of E sub s function that we know, and so we average over that function. So this situation where our identical copies are of a subsystem in equilibrium with a reservoir at temperature T is called the canonical ensemble. And so that's why we call the corresponding partition function the canonical partition function. Okay, so it's super interesting to note that in reality, we don't have all these copies. These copies are a computational artifice. In reality, if we have a physical system, what we do is we make a bunch of measurements over time as we do sequential measurements. And so a really important question is, does the time average in the real world always exactly equal the ensemble average that we do in this kind of thought experiment? And can we use fancy math to prove general results about the correspondence between time averages and ensemble averages? So this is an important research topic. It's both a physics topic and a mathematics topic, surprisingly. And very little is known generally, though of course as physicists we're pretty sure that this is true in many, many cases. I think it's interesting to actually try to figure out cases where it's not true and understand why. So, one more thing. The Boltzmann probability actually gives us another way to think about temperature. So the canonical Boltzmann probability lets us define temperature by noting that if we could measure a physical quantity, an experimental quantity, that's proportional to the probability of finding a subsystem with energy epsilon, then the temperature is the inverse decay length of that exponential. And you actually use this quite a lot in experiments. I do it in my lab. You're going to do it in your early in the classroom activity, which you should be already planning. So this is actually real physics that comes up all the time. And that's our point of doing early in the classroom, is we want you to touch the real physics and not just have to do derivations. So please make sure that you've been in touch with Neelam to start planning your early in the classroom experiment. I think it's really rewarding. So you're going to make measurements of light-emitting diode emission spectra and understand how to connect those to Boltzmann probabilities and use the Boltzmann probabilities to measure the temperature at the junction of the LED. Yeah, sorry, I messed that up. Right, so here we are with the most important results probably in the whole class. We have the Boltzmann probability, which is a Boltzmann factor for energy E sub s, divided by the sum over all Boltzmann factors, which is the partition function. So the partition function is really important. It not only normalizes the probability, it has a physical interpretation that it counts relevant states at a given temperature. And so these probabilities allow us to compute any averages that we need, and that's called ensemble averaging. And so the next time what we're going to find out is that you can use this function z alone to calculate all of the thermodynamics that you need. So it's actually really surprising that this normalization factor is not just a mathematical convenience with some interesting physical intuition, but it's actually an extremely versatile tool.